Hi there, and thank you for joining the Change I Am Possible podcast. Do kindly subscribe, support, and share. So, today I have with us John Martinis. He's a physicist and a professor. He holds the Worcester Chair in Experimental Physics at the University of California, Santa Barbara. Until recently, he was the head of the quantum computing hardware at Google's Quantum AI Lab. So John Martinis was the driving force behind Google's quantum supremacy announcement using a programmable superconducting processor. So quantum computing, once mature, could be transformational to mankind, as unlike the classical or regular computer, which uses binary code, quantum computer uses the properties of quantum physics, the source code of a universe to function. Atoms. The quantum computer can be extremely advantageous for certain tasks and could vastly outperform even a best supercomputer. Is quantum computing the next revolution of mankind? Do enjoy the conversation.
So, John, tell me, quantum physics is where you start if you want to understand the universe, right? And then quantum mechanics is the fundamental to building a quantum computer. So let's start there. And let's please explain to my audience why is the micro and macro world so jarringly different. So quantum physics, it even challenges how we perceive or physical reality, right? So then there is this the properties of quantum. There is quantum entanglement, quantum superposition, which have left some of the greatest minds confused, right? So can you help my audience understand the weirdness and the fantastic nature of the quantum world?
Yeah, and as you say, the macro world that we're accustomed to is very different to the micro or nano world, maybe more precisely. And it's kind of a different set of laws. And first of all, I think people have to realize is if quantum mechanics didn't exist, the world would not be at all like we're here, and we would not be here. So quantum mechanics is fundamentally very important for understanding, say, how atoms and molecules work. And I like to point out the fact that if quantum mechanics didn't exist, atoms would have no size, and we wouldn't be here. So what's going on there? Well, I think most people know that in atoms, you have a nuclei and electrons that are around the nuclei. And let's just take the hydrogen atom for simple, but all the other atoms are the same. So you have a hydrogen atom and an electron, and they attract each other through electromagnetic force. And if you just think of these two particles just attracting each other, they'll just come and attract each other and then, stick to each other. And again, they won't have any size. These are more or less point particles. So why do atoms have size? And that's because it is micro electrons obey quantum mechanics, so no longer a point particle. And in fact, they form some kind of cloud around the proton. And in some sense, they're at all points around the proton at the same time in this cloud, giving it some kind of cloud around the proton and giving it some size. Okay, so it's a very unusual aspect of what happens to physics at small time scales, and these fundamental particles have this kind of cloud behavior. Now, what's interesting about the cloud behavior is you kind of think, well, it's kind of randomly positioned all around the proton. It really doesn't work like that. It's actually in what physicists call a wave function. So it's more or less like a guitar string, where there are these standing wave modes, like a guitar string would be vibrating in this way. So there's kind of a wave mode of the electron around the particle, and that wave mode and the standing wave puts it into very, very well-defined states. And these well-defined states are extremely important because you can calculate what they are. They can make transitions from well-defined state to another well-defined state. And because of that, it's very, very precise, but because of that, you can actually do computation on those states, and thus you can build a quantum computer out of it. And of course, fact that you can obey computation means that if you do calculations on how these clouds work, it's very, very precise. It's mathematically, you can figure out what's going on. And thus physicists are able to predict what's going on in nature. And then being able to predict that, you can also use those properties in the end to do this new kind of computation.
Right. So sticking to the quantum physics part, I mean, the double slit experiment, this was Niels Bohr.
Yes.
Back in the early, it posits that atoms do not exist. How do you wrap your head around something like that? And what's your view on something like that?
Yeah, so for the, again, this electron is not a point particle, which if you have two slits, and an electron can go through one slit or the other. In fact, if you set up the experiment right, it forms like this cloud or this wave function that many things, and it can go through the two slits simultaneously on both sides, and then come out, and then depending on the angle it goes through, the waves can either constructively interfere, making it bigger or making it more probable, or destructively interfere, bringing the wave amplitude down and making it less probable, which is why when you look at the electrons going through, there are bright spots and dim spots on the other side. And again, it's the wave nature of the electrons, their vibrating nature, and sometimes they vibrate together and sometimes they vibrate against each other, getting either something bright or something dim. And again, this is very precise. Knowing your experimental configuration, you can calculate what's happening very, very precisely. Again, quantum mechanics is a very well-defined mathematical object, very well-defined physics.
Right. So you're saying there's no woo-woo around there because the media says, it depends upon a conscious observer. So there's no woo-woo around there. You're saying it's...
Well, some people think that way. Right. And, there's still a lot of questions about, what are the assumptions behind quantum mechanics. And for me, it's more like you have a well-defined mathematical equation and rules. And, as long as you don't ask where the rules come from, you just say, nature gives us those rules, you can then be okay. But I agree, those are interesting subjects and interesting things of where the rules come from. But for me, I guess I'm kind of a pragmatist. It's like, okay, we have those rules and that's the way nature works. And then you predict experiments, or you can build a quantum computer and you can use that, once you know the rules. And of course, finding out those rules a century ago was what was really hard. And, a lot of brilliant people, figured out. And yeah, like you say, to this day, they're kind of strange rules. And, we still try to understand them.
So till recently, you were part of the team heading the quantum lab at Google with Hartmut Nevin heading the software part, right? So can you please talk about your experience building the quantum computer at Google and the much talked about Google Quantum Supremacy?
Yeah, thank you. Well, just to give you a little bit of history, I started making superconducting qubits back in mid-1980. I was a graduate student at Berkeley. And then we were just trying to get a single qubit to work and seeing quantized energy levels, really simple experiment. And then throughout my career, I've been interested in quantum devices. And then once the idea of building a quantum computer came into the forefront, let's say mid-1990s, I started working on that kind of full time. So I started in a government lab in Boulder, Colorado at NIST, and then I moved to UC Santa Barbara in 2004 and had a group there. And we were just building up more and more complex qubit systems, as well as many other people around the world at that time, during that time. And then towards the end of my UC Santa Barbara time, we started understanding how to build a quantum computer system, actually how to build a computer. Initially, we're just trying to make qubits, get them to couple together, just understanding physics. And then with some people, we wrote a paper and really started to understand how to build a computer. So we started in UC Santa Barbara building a quantum computer, initially with 5 qubits on a line, and then eventually with 9 qubits on a line, okay? And that enabled us to do some nice experiments, get the qubit devices working properly, and getting them to work with very low errors, and ran some nice algorithms, did some things. So at that point, we were very excited, and we actually wrote in our papers how to make a 2-dimensional grid. So instead of a line, kind of like a checkerboard, 2-dimensional grid. And the 2-dimensional grid is what you needed to build a full quantum computer. And that's what the theories have told us. So, you know, we were thinking about how to do that. And then Google, you know, was doing some research using a D-Wave quantum computer. And I was involved in some analysis of that machine. And Hartman invited me to give a talk at Google. It's still on YouTube. You can read that, where I talked about the 5-qubit experiment. And afterwards, we started talking, and basically, they wanted to build a quantum computer, and I wanted to build a quantum computer, and we talked about it, and we decided, you know, that would make sense. And I would say what really made sense at the time is that we were doing nice research on a university, but, you know, students and postdocs come into the lab and get trained and then go. And if you want to build something as difficult as building a quantum computer, you kind of need people to stick around and get more experience and figure that out. So, you know, at the time, we kind of realized we thought we knew how to build it, and at least we knew what to do next. And then we moved to Google, and people could stick around and get better and better doing it. So it seemed like the right move to go to Google. And this was very nice because the university was very understanding. They understood that, well, it's a sign of successful research, right, for industry to get interested. So I moved to Google, although I still have a position at UC Santa Barbara, and I took on students. And students and post-students, when they graduate, and postdocs moved to Google, and all my students graduated. And then we started building this 2D array. And then about, I don't know, maybe it was 3 or 4 years ago, the theory group came up with a proposal to do the quantum supremacy experiment. And then I thought this was really interesting and fun and exciting and challenging. And so we kind of redirected into the quantum supremacy, but it's kind of what we wanted to do anyway. It was a very, you know, distinct experiment we wanted to do on the road to building a bigger quantum system. So what was so interesting about the quantum supremacy? Well, basically you had to make, you know, 50 to 60 qubits and run the qubit logic operations for 20 or 30 cycles deep. So it was about 1,000 operations or so. But the particular algorithm was such that when you ran the algorithm and you got some output, in order to check whether the output was correct, you had to check it against a classical simulation of the quantum mechanics of this, which people do all the time. But the problem classically is that there's so many operations that it really begins to tax even the largest supercomputer on. So it's a very well-crafted, chosen problem where you could do a quantum computing, and then you can check that, run it against a classical computer to make sure everything's running right. And we were able to make the system big enough and work well enough. So at the end, taking data in 200 seconds or so would have taken, you know, 10,000 years on the biggest supercomputer on Earth in order to check that properly. And of course, we could do smaller systems, and the checking time would be short enough so we knew the quantum computer was working, and we can do a whole host of checks to make sure we're getting it and checking the answer. And then finally, we made it big enough where you couldn't do it. So you know, that's the experiment. But what's really interesting is, like, why is this an important experiment? Okay. And I would say, and partly, it's kind of almost a marketing experiment, in the sense that for years and years, physicists have been talking about how a quantum computer, in the way that it operates with this 0 plus and 1 state at the same time, it's kind of like a parallel processor, very, very fast parallel processor. And that would give you this huge amount of computational speed up and advantage. Well, people have been talking about that for, 30 years or so, but, well, no one had done the experiment. So it was the first experiment that said, look, here's an algorithm, here's a definite thing to do. It's not useful for anything yet, but let's just do that. And you show that it's powerful. And thus, Silicon Valley executives, okay, quantum computer is not just pie in the sky, pipe dream of physicists that maybe some way we'll get it to work, but it's really coming. And that, you can imagine that, okay, things are improving over time, and now it's a time to, get interested in it, invest in it, really try to get this work, because it could be coming in some time. So I would say that was very good. And again, we've seen a lot of positive response and a lot of interest in the field, because again, it's working. I would say it's almost like the physicists are kind of convinced that quantum mechanics will work and everything will be fine, but you kind of have to convince the engineers, right? And the business, okay, this really works, and you can really do it. I would say, so that's kind of from the engineering or business point of view. In terms of the physics point of view, I mean, you write down the physics theory that says this should work, but, since you're putting it together in such a different way, you don't know if it's actually going to work, in the way you expected, because it's so much bigger than anything anyone has done before. So a lot of this experiment scientifically was that, yes, the science works, the physics works as we expect. In fact, if you look at the error rate and details of it, it works fantastically well, okay? And you can predict the errors of the machine from very simple measurements. So we know that a lot of the details of how the error works in a complex machine is proper, and the assumptions people have made are pretty good. So again, it gave you a lot more physics justification that this thing was really going to work. And again, that's very powerful.
Lovely, superb. So first of all, congratulations. I'm sure this will go down in history. We're talking at this point in time, but I'm sure in the coming few decades, this will definitely go down in history as the first quantum supremacy attained, right? So
we are happy to such a groundbreaking experiment. That was really fun.
Yeah. But I mean, I'm sure you got this so many times. There was great press coverage, but on the other side, if you see that the community remained skeptical about it. People, I mean, like IBM or people like Scott Aronson were quite skeptical. So your views on that?
Well, when you do, which we think is an important experiment, we like skepticism. We want people to check the experiment and make sure it's right and to look at it carefully. And there's been quite a couple people who have really tried to look very carefully, and that's good. That's what you should do in science. So this is great. Now, I think Scott Aronson has been not skeptical at all. He's written blog articles and even a New York Times editorial, and he did some prior work on what was equivalent to quantum supremacy in the theory prediction. So he was fine. IBM, IBM's a competitor. We expect them to be, say things. It's fine. Their whole thing was that they had an alternative algorithm that could run it way faster than 10,000 years. What I thought was all kind of funny about this is they proposed an algorithm. It was just what's called a white paper. They actually didn't run the algorithm, right? So they made it's kind of like people thought that they actually ran it, but they didn't. And we're looking forward to some day where they actually run it. But when we talk about computer science algorithms, when you talk about experimental physics, you need to show the data. Okay, so they showed a nice proposal, but they didn't show the data yet. And, you know, we expect in the next year. The interesting thing, though, is that they're going to have to work really hard to run this on Summit and do everything. All we need to do is add 4 qubits, and it will be unsimulatable with their algorithm. And, you know, we've got 53 to work. We can get 57 to work. And in fact, there are a newer generation of devices so, okay, we're trying to have a little race right now to see whether the hardware is going to be first, or is it going to be the software, or whatever. Both ways, you know, I think we can still claim that this is pretty amazing.
Right. So you know, several recent efforts are looking for quantum phenomena operating close to room temperature, claiming that any realistic computing technology should operate at normal temperature. So Google and both, even IBM, is focused on superconducting qubits. So what's your take on trapped ion and photon-based qubits?
Sure. You know, there's a really interesting thing when you hear about all the different systems people are looking at, is everyone says that their approach is the best. So I think superconductivity is best, and you can look at our particular implementation, of course, it's best. And I can rattle off a bunch of technical things, and so can everyone else. So these kind of statements are always kind of amusing for me, because, you know, we're proud of our systems, and that's great. In the end, what you have to do is do an experiment, and not just show that a few qubits work, but show a big system array and get all the system engineering right. And all I would say with these other proposals is, yeah, that's great, but, you know, do something like the quantum supremacy experiment, which is really complex and hard, and then we can start comparing. But, you know, at some point in the future, these other approaches may just pass by and be better, or maybe not, and I just need to see it. But I would say this point is, I think what's very interesting about our field now is that we don't have to speculate theoretically or whatever. We can just look at the data and look at the results. And then, you know, that will speak for itself. And, you know, the basic thing here is it's very subtle to get a quantum computer to work kind of system-wide. You can get elements of it to work, but nothing in the system is particularly hard for a quantum computer, and thus the only way to know whether you really understand how to build the system is to build it and see that it works. And we're in a nice era now where, you know, we can wait and see, and, you know, see if everyone's claims really are true.
Right. So when do you think we will have a working quantum computer? When will, because right now the Google has come over somewhere around 53 qubits. When do we have a working quantum computer? There's so much hype around the possibilities and potential of a quantum computer. You know, they say when we have a working quantum computer, we will have unhackable internet, protein folding, quantum-proof security, cleaner fertilizer, and so on and so forth.
Yeah. So right now, we're really at the very beginning of a long road to build a quantum computer. So the quantum supremacy experiment is a quantum computer. It just can't, you can run one or few algorithms, okay? And that people are beginning to run other algorithms. There were 2 papers submitted by the Google group recently to run 2 other algorithms, one on chemistry and one on some optimization problem. But people are doing it. But these other problems are not something you can't solve on a classical computer. Okay? The real interesting thing is what happens, what do you want to do to start solving problems that you can't solve on a real computer, that are real world problems, okay? Now, there is some thought and some hope that you can do that without what's called quantum error correction. And you might be able to do that in the next few years by making like our 53 qubit scale device, make it lower errors. And other people with a modest number of qubits can do that. So there is some hope to do that, but it's not quite clear. However, if you make a big enough quantum computer where you can detect errors in the quantum computer and correct them, just like it's somewhat similar to what goes on with the classical computer, where you have error correction protocols. If you do that, then you should be able to solve some problems. So building a error correction quantum computer is very hard because, first of all, you have to make your qubits have lower errors than they have now by, let's say, a factor of 10 or so, which is, fairly significant, but people think they can do that. And then you have to make many, many qubits in order to get this to work. And the present estimates are about 10 times better than what we do now, and about 100,000 to 1 million qubits.
Wow.
So it's however, if you look at your computer in front of you, that's many, many billions of,
right.
It's whatever. Okay. And when I was a kid, you had computers that, personal computers in the 70s had maybe 10,000, 20,000 bytes of memory. They didn't have any memory at all. So, it's really possible to do that. We just have to give it some time. So, we have to go on this long road to make our qubits better, to make more and more of them. And then what was interesting at Google, after we did the quantum supremacy experiment, I started thinking about, well, exactly how could we build 100,000 or 1 million qubits? Again, we have to make our qubits better. And I came up with a pathway to do that. So I call it a pathway as I could see exactly what we needed to do. But of course, there was technology to build along the way, but it seemed reasonable to me. So I'm actually excited that it may be possible. And surely I think the pathway is good enough so that, you should invest the money and do this. But we will have to see if it's possible. Of course, other people are thinking about it. And we'll have to see if those pathways and those ideas will come. So, and the time scale that we're talking about here, Hartman has talked about roughly 10 years as a time scale to do that. It's a lot of things to invent, so maybe it's a little bit slower than that. We'll have to see. Maybe a little bit faster, you don't know. But it's a significant effort to do there. But we think we know enough now to really know what we have to do. And that's kind of nice about the quantum supremacy experiment, is that we figured out enough physics that, okay, we know what we have. First of all, we know what we have to improve, but we kind of could see how this thing could work. And some of the fundamental engineering constraints we started on.
Right. So this pathway that you're talking about, which can help you build better quantum computers with better qubits, better error correction, and no noise, would you continue with this this thought with your university, or are you looking at another organization to join?
Yeah. So I left Google a month and a half or so ago, and the program was going very well, and everything was fine. The young people in the hardware group wanted to get out of my shadow, and there's a lot of tension there. So the best thing for me was to leave. And I'm glad, because they have a very clear pathway forward. And maybe I'll get involved in some of that, maybe not, we'll see. And then what I'm doing right now is I'm looking at a lot of opportunities and trying. I have a series of opportunities that look interesting to me. And I'm trying to decide, today, right now, to figure out what are the best things to do for me. And we'll see. But, I would say, in Google, I was trying to think, well, how would Google make the quantum computer? And after leaving Google, I'm trying to devise opportunities so that someone can build a quantum computer. Because now that I have a specific example, I think I can go out and look at what other people are doing and take the knowledge from my specific example and apply it to the different things that people are thinking about. And there might be something fruitful and interesting there. So I'm looking at things. It's actually an interesting idea to take my experience and try to apply that. And then we'll just see what happens.
Right. So the Indian government has recently announced a $1 billion program for quantum technology. So what would be your advice for scientists, engineers, and policymakers over here on how best to spend your money? And would you be open to kind of help the Indian scientist community build a better quantum computer?
Yeah. So first of all, one of the things that I want to do now on my own is to go and spend time, kind of like a sabbatical at different universities to talk to people, talk about what I know, see what people are thinking of, and trying to help the community to do that. So I already have a couple trips planned, long visits, and I imagine I can do something like that. That's certainly interesting. And of course, it's a nice way to visit a country and learn about the local culture. And our kids are grown, so it's not too hard for my wife to do that. And then, it's really interesting because I think what I like about quantum technologies is it's a very good research subject for students in the university and professors. You try to understand something very fundamental of quantum mechanics, but you're building something at the same time and trying to do some practical things, building a sensor, building optical communication, building a quantum computer. It's good mix of basic science and trying to do something applied. And, it's always hard to figure out how to balance that. But I think it's a really excellent training ground for students to, and to build up the technological base. In my field, you're going to have to learn about low temperature physics. You have to learn about microfabrication, which is a very good technological skill for people to do. So the most exciting part for me is that your country is willing to do that, put the money into it, and it's a good way to invest money in doing that. That said, I think the most exciting thing that may happen in the next few years is people trying to build systems, quantum computers, that's pretty hard, but also communication systems and sensors and other things, which has industrial relevance. And, it would be good to, these more academic groups that have ties with these more practical groups, because I think the combination is good. And that's, for example, myself, I kind of have a practical mind, but I like basic science. But I find that the practical applications really focuses my mind on what are the important fundamental issues to deal with. And this is kind of what happened with the quantum supremacy experiment. It's a fundamental physics, but we had to do that, and we had to learn a lot from that in order to higher and build my computer. I would say kind of balancing, those two things, academic and practical things, is something I think that's important to think about.
Right. So do you see quantum computing playing a role in taking the artificial intelligence ecosystem forward? At this point in time, we are at the artificial narrow stage. Would leveraging quantum computing be the step towards the artificial general intelligence that we are all working towards?
Yeah, so when I was at Google, I belonged to the Quantum AI Lab. So, in Google, of course, artificial intelligence and deep neural network and learning was a very important part of the company. And the theory group was very much interested in algorithms in that way. And, people at Google and other people are thinking about it. And although I'm not an expert in this field, for example, Hartman Nevin has been working on that for many years. He saw a lot of parallels between, classical artificial intelligence and neural network and learning and quantum mechanics, and thus got interested. So people are working on it, but they're still kind of developing what's going on, and it's going to take some more time to see how well that will pan out. I mean, part of the issue here is in conventional artificial intelligence that has been proven very successful in the last, let's say, 10 years or so. It requires lots of data and deep neural nets and big computers to do it. That's part of the reason it got to work. And right now we have very small quantum computers. So it might take a little bit more time till we build bigger quantum computers to get that to work properly. But it's still worth doing research. And, the whole AI neural net community, that was around for many years until they finally got a big enough system to get it to work. So, so it's interesting research and needs to be done. And I'm sure, people will make progress on that.
Right. So the last question of the day, and just going to go a little off track. So Seth Lloyd, he's the professor of mechanical engineer at physics at MIT. He said the universe is a quantum computer. Geordie Rose, ex D-Wave, in a talk said that we will be able to access parallel worlds when we have a working quantum computer. Max Tegmark says the universe could be mathematical. Then recently there was this TV series, it's on Hulu, I believe, and Alex Garland has directed it. And I believe David Deutsch is the scientific advisor for that TV series. The basic of the TV series is that there's this company which has built a quantum computer, and they've built this algorithm with which they can access the past, present, and future. So are we living in a simulation?
So people like to speculate a lot about quantum computing, and I think that's very wonderful and nice. And like there's this latest Star Trek series called Picard, where they have a quantum computer and do some nice things. And this is great. And I would say we really don't know where exactly this is going to take. So, it's fun to speculate. I'm an experimentalist. I work in the lab. To me, this is a machine. It's kind of like a gigantic parallel processing machine. So I think about a big supercomputer, but instead of it filling a room, it's kind of a desk-sized machine, but it's a gigantic parallel processor. But I think of it much more like a conventional computer than all these nice things. But I don't want to spoil anyone's fun. I mean, I think it's cool to speculate. And we are accessing a part of the universe through the superposition of states that we've never been able to access before. And the quantum supremacy demonstrates that, it really does exist. And I'm not sure that it's going to represent itself in quite the time travel or whatever people are thinking of. But it is kind of a new resource, and we don't know exactly where this is going to take us. And just like in classical computers, people had a few ideas what to use a classical computer for when they first made it. And it's way beyond that now. I mean, we have to build machines and play with them, and then we'll see. And my guess is its application will be different than what we expected, right? Because that's what human creativity is all about. And that's what's, of course, interesting and fun about doing the research. You really don't know.
Lovely. Thank you. Really appreciate you being part of Change I Am Possible podcast and sharing your insight. And like you said, I mean, we're living in exponential times, and the future looks super exciting. And we are at the cusp of just discovering these amazing technologies which could transform mankind. And we need to spend more time on these kind of technologies, understand it better, help it grow together as a community and push it forward. So tomorrow we build a better world, we build this technology and scale it to a point where it can help us all. So thank you, John, being part of Change.
Yes, and it's very fun to work in this field exactly because of that sentiment. So thank you for saying that so nicely.